All right, here's the warm-up for the day. Since so many people are looking at devices, did the midterm grades officially get released? Did you get an email? Yes, okay, thank God. I sent I'm walking over to the lecture hall. Let's hit publish on this. Okay, well, here's the warm-up. We're gonna talk about this first. I know your brain is on midterm stuff, and then we can spend as much time as we would like answering your questions and talking about the midterm after the warm-up. So go ahead, walk through a BFS of this given graph right here, and we will talk about it in, let's say, 3 minutes. All right, in the interest of time, let's chat about this BFS. So, remember that BFS stands for what? Can anyone tell me what BFS stands for? We remember from Wednesday, maybe? Yeah. Breadth first search. Emphasis on the breadth. Different from depth first search, right? So breadth, it's about exploring all of my neighbors before I go on to explore neighbors of neighbors. I like to think of it as sort of like rungs of proximity. We start at the source, and we kind of branch out in a breadth way until we eventually get to target. Different from depth first search, where that's where as soon as I see my first neighbor, I then explore that neighbor's first neighbor and that neighbor's first neighbor down one long path all the way to the bottom of the graph, and then it kind of comes back and cleans things up. So we're doing a BFS in this case. So we're going to start at the index of 1. Which neighbor of 1 am I going to visit first? 2. And the reason we're visiting 2 first is because I specifically have this break ties between unvisited vertices by visiting the smaller vertex first. Technically in BFS, it is correct to visit either 2 or 4, but since I have to have one correct answer so I can grade y'all on that type of way, I'll always give you some type of tie break like this. So we're going to visit 2 first. Let's see, I think I have animations. So we do 1, then we do 2, and then we do 4. Okay, these animations may be messed up from here on out, but we're going to see how it goes. Now, where do we go next after we go 1, 2, and 4? Yeah, in the back. Yes, so because 2 comes before 4, we're going to explore 2's unvisited neighbors, which right now is what number? 5. Okay, I'm pretty sure these animations are incorrect. Oh my gosh, okay. Oh, it was close-ish. Somebody that works at that company, Google, should really fix the animation features on Google Slides because they are a hot mess. Sincerely, a former Google employee and PowerPoint employee. All right. So we go to node 5. Then we go to node 3 because that's 4's neighbor. Then we go to the neighbors of 5, which are 6 and 8, and 6 is smaller, so we do 6 first. And now, finally, we have to go to the neighbors of 6. So what is the next number we need to go to that I haven't pressed the animation on? What's the next one? Second to last. Anyone? 7. I agree. 7. All right, there it is. Okay, and then 9. There we go. Does anyone have any questions on that ordering? No. Cool. Great. Okay, because everyone's like, we don't want to talk about BFS right now. All right, okay. So extra. All right. We want to talk about the midterm. Okay, let's talk about the midterm. So you should now have your grades back. I want you to know this is a very well-scoring exam. This is actually pretty high in average because remember, you have the resubmission. And so if the median is a 66% before the resubmission, and frankly, all of you seem to do very, very well on the resubmission because you can talk to each other, and you can talk to TAs, and you can go on the internet, and you can sit in the comfort of your own home and assess your choices. You tend to do very well on the resubmission, and so when we average the 2 together, I'm guessing that our overall median is going to end somewhere in the 80s. Which my colleagues think is absolutely blasphemous, but I've decided is a totally reasonable median score for an assessment. There were some questions that certainly were harder than others. I know design is tough, obviously, but that's also why we think it's interesting for you to have a chance to sort of rethink your things and resubmit them. You know, if it was a really obvious and easy exam, it would be silly to have you do a resubmission. The total scores out of 80. The resubmission assignment is on Gradescope, so you will do that digitally, so you don't have to deal with writing anymore. It should be open now. I think it auto-opened at 3:30. It will close a week from today on Friday, 2/16, and I cannot accept late assignments on that one. I have to have your resubmission no later than Friday, 2/16, because then the TAs are going to grade it, and then you're going to get your final score, and you're going to be like, Casey, we don't get our final score on the midterm until week 8? Yeah, or I could, you know, just force you to keep this score, right? We don't want that. So please, please, you cannot use late days. I will not be able to accept late submissions on 2/16. If you have something going on in your life right now, hopefully we're already talking, but it will be very difficult for me if you send me an email on 2/16 that's like, hey, I've been really stressed and I didn't get around to it. My answer will probably be no. I cannot give you an exception on this particular assignment. But we are happy to help you in any way we can be as successful as possible on the resubmission. So it is an individual assignment, and you should know that, yes, I do run comparisons between all of your answers because we live in the future, and that's just a button click for me in Gradescope. You can talk to the TAs about this. You can ask a TA to clarify maybe why you got the score that you did get on the original midterm. You can talk to the TAs about concepts on the midterm. You cannot ask a TA to pre-grade your submission, though. So, for example, do not ask a TA, is this correct? Will this get full credit? For somewhat obvious liable reasons, that puts us in a really sticky situation. So save your TA that discomfort and reframe your question to be about, I'm thinking about the runtime of hash tables in practice. That's a totally fine question to ask. Not, is my hash table correct? You're welcome to speak to one another, but the same academic misconduct stuff applies as usual. You are responsible for your own work. You're responsible to know everything that you put down on your piece of paper. Do not show your exam to other folks, and do not look at other folks' paper. Usually that, as long as you have to explain it verbally or in some way where you're not just looking at stuff and copying it down, that usually saves you from some of the icky academic misconduct stuff. But you're welcome to discuss concepts. I know I couldn't stop you from doing that anyway. We also, and by we I mean really mostly the TAs because they are the heroes of the hour, they put together a whole Google Doc with common student mistakes, question by question. So as you are reviewing your grades, also take a look at this Google Doc and see if maybe it was how you worded your answer, maybe you didn't give us enough information, et cetera, to make sure that you are giving us exactly what we want so we can give you hopefully full credit on the resubmission. And also, if you're trying to figure out how to ask the TA about something, you can ask them about anything on the common mistakes, because that's like a general, we're not talking about your answer, we're talking about general mistakes. You can talk to the TAs about anything that's in that doc that you want. Questions, concerns, feelings, anything we want to chat about. Yeah? For half credit that you missed back, yes, exactly. So if you got a 60 and you get 100 on the resubmission, you'd end up with an 80. That's it? That's the only question? Usually I have to stand up here and defend our choices for like 15 minutes. Yeah?
So for the regrade thing, is there a way to just like regrade one?
Yeah, you don't have to, so you should be able to select which questions you want to resubmit. So for example, if you did really well on a question, you're like, great, I don't want to change that score, you don't have to resubmit that one.
Not the resubmission, the regrade. It says midterm regrade.
Oh, thank you. So regrades, if you think a grade has been incorrectly applied, we will let you, of course, make your case, and you should always make your case, but we are going to wait to open regrade requests for the midterm and the resubmission at the same time. So sit on your notes, think about what happened in your midterm. If you're at all confused about why you got the score that you got, feel free to talk to a TA in office hours or post it in private on Ed or send me an email, all of that good stuff. And then once we grade your resubmission, we'll give you your resubmission grade, and you can then submit any regrade requests both on your original midterm and on the resubmission at the same time. Yeah, sure.
Didn't that affect the score on the resubmission? Because the grading of the original was wrong. You want to fix that so that you get more?
So we grade the resubmissions totally independently. It's as if we've never seen your other exam before. So we grade them independently, and that's also part of why we just do all of the regrading all at once, because then we're just done with this assignment. But yes, it would certainly alter your final grade if you got incorrectly graded on the midterm. And of course, we are happy to fix that. Yes, thank you. Good clarifying questions. Sure. Thank you. If you took the exam in class on 2-2, that is the one that you will resubmit through. If you don't know what the makeup midterm one is about, it's not for you. That's for someone else. So don't even worry about it. Any other questions so far? Oh, yes, thank you.
Is there any way to access an answer that wasn't scanned?
Oh, okay, there are 2 students who that applies to, and I had to take physical pictures of the back of their papers. If that's you, come talk to me, and I will find you. Also, just so you all know, I have your physical exams still. I have to legally keep them in my office until the end of the school year. So if you want them, you can certainly have them back, but they are all alligator clipped with Post-its and all this wild stuff in my office. So if you want to look at your physical exam, you are more than welcome to. Maybe send me an email so I can make sure that I have some time to dig it out of the box and give it to you. Especially if, for example, there's something maybe that was on a back side of the page that you don't think was properly graded. I'm happy to find that exam and make sure we'll correct that for you. Anyone else? Okay, cool. Like I said, this is honestly, this is a pretty good score. If we end up with 80s, something in the 80s on our overall median, you're doing pretty well. Okay, great. And then, of course, reminder, what is it? Is EX4 out officially? Yeah, and I think that's due on Tuesday, right? And so their midterm resubmission will be due Friday. Your P3 will be due Thursday, and your EX4 will be due Tuesday. I'm sorry, there's so many things colliding, but hopefully we gave you a little extra wiggle room because EX4 is a little shorter, and P3 is also a little shorter. Okay, all right. Shall we learn something new then? So on Wednesday, we met our first graph algorithms, BFS, DFS, and topological sort, which you'll often hear me refer to as topo sort. And today we are learning what is maybe the most popular, the most useful of the graph algorithms. You could argue. We'll pick up MSTs next Monday, but we'll see how that goes. So let's start with the problem. So we had previously talked about the connectivity problem. Can you just find any path at all from a graph from a source to a target? But now, what if it's not just about the presence of a path? It's instead about the most efficient way to get from one vertex to the other. We're looking for the shortest path that causes connectivity. Now, it depends on the type of graph we have. Let's say we have an unweighted graph. So we have edges, but they don't have any values associated with them. Well, how could we possibly solve this? Well, I think I sort of gave it away last Wednesday, but we could use BFS, because those sound like pretty similar problems, right? I'm just trying to get from a source to a target. But in this way, I want to kind of do it as intelligently as possible. And since there's no weights, in this context, we're going to determine shortest path by the fewest number of edges to traverse. Or if you're thinking of yourself as an island hopper, the fewest hops between vertices to get somewhere. This is also a kind of the equivalent of deciding that the path is of each path has a weight of 1. Like every edge has the same weight. We're just trying to travel in the least amount of edges. So what we can do is we can take BFS, which is all of the unhighlighted code, and we can add a couple extra structures to keep track of some information as we go along. The information we're going to want to keep track of is what is the current distance that I am traveling as I'm figuring out this path, so I can tell if it's shortest or not, and also what is the actual path I'm going to take? Because the goal is to tell what is that path. So I need a sequence of vertices to tell me how I would travel through the graph with the least amount of jumps possible. So we're going to add 2 maps to our code here. And like I said, a lot of graph code just starts to look like this, where we just keep adding maps and adding extra structures in to hold extra information as we're going along. Very common. So we're going to do this in forms of 2 maps. The first one, edge 2, is going to tell us between this edge and the one I should travel that represents the shortest path. So eventually, when this map is full, it will tell me what the shortest path is. And then the distance 2, that's keeping track of how far I've walked already, what that total number of jumps is, so that I can use that to compare and make the most intelligent decision. And in fact, if you can see here this +1, this is how we're calculating the distances. Every time we travel to a new vertex, we just add 1 to the distance. It's the same equivalent to saying each edge counts as a weight of 1 or a distance of 1. The start we put in as not having any previous vertex coming from, that's the start. And the start has a distance of 0 because I haven't traveled anywhere so far. So I initialize the source target to have nobody coming before them and a distance of 0. And then as I just do my regular BFS work, whenever I finally accomplish a visited situation, I put in that that vertex and the edge that took me to get there, and then I count that distance by adding 1, because that's 1 hop. The run time of this ends up being the same as BFS, because it's BFS code. I'm just adding a couple structures that keep track of information as I go along. And BFS code, it's doing that crawl, right? And so it's going to explore each vertex by exploring each edge. And so we think of that as graph linear runtime. But because we have 2 variables, we would say this is O of V plus O of E time. That's just the graph equivalent of O of N. We just have 2 variables now. So this runs in what we call graph linear, O of V plus E. Questions about this unweighted shortest path? Sure. So what will happen here is if you find a shorter path as you're navigating, it will overwrite a little bit, because you can see we're sort of doing it as we're standing on a vertex and looking at our neighbors. That's how we're calculating the distance to them. We're not actually putting it in the map up here, which is when I actually sort of island hop to land on top of that vertex. So the distances are dictated when I'm standing on, let's say, source, and I'm looking at my immediate neighbors. Those will initially be put into the graph with, source as the edge from and 1 as their distance. And then their neighbors would be, like if it goes source and then a vertex A and then a vertex B is the neighbor of A, B's edge 2 would be A and its distance would be 2. And we're doing that here because as we navigate through, we may, before we actually hop and land on a node, find a shorter path, and we do want to override that. That will make a lot more sense, I promise all of you, when I get to the next algorithm. And I'll do it with numbers, and it'll be a little clearer. So here, let's walk through it. So let's say we start at A. Its dist2 is 0, because we haven't traveled any distance so far. And then we look ahead and we say, oh, B and C, we're going to now give them a distance of 1 because they're 1 hop away from source. And their edge 2 will be source, meaning the thing that comes right before them is source. We then explore another level out. D is connected to both B and C. D gets a distance of 2. And we're going to pick B to be its edge from. We're just going to break ties alphabetically here. It kind of doesn't technically matter since they both connect to it. But the way that I would create the path to D then is I would say D connects to B connects to A. And that's the path. And right now, that's actually the shortest path to D. But we're looking for the shortest path to E, and we have to finish that jump. And again, we just add 1 into the previous distance, which is the one at C, giving us 2. And now E's path is working backwards. E points at C, C points at A. So when you are finally ready to report the results, if I'm like, okay, give me the shortest path from A to D, you would look up D in your map, and you would see that D's edge 2 is B, and then you would look up B's edge 2, and you would say it's A, and that's how you recreate the path. You kind of start at the terminus and then jump through the map to recreate the path that gets you there. Yes?
Do you have anything to see what the edge 2 actually looks like? Like what is being returned?
I mean, it would be the edge 2, since it's a double, it would be a single double value in this case. We made it double in case they were, double values, but frankly, ints are what is happening here. Yeah. Yeah.
If there was a bunch of funny business past E, would it spend the time looking through that path or would it stop once the distance?
Ah, this is a good question. So I'm going to alter your question to answer what I really want to answer, because there's two questions really contained here. I think your question is, well, what happened if we were looking for the shortest path to E, and then there was a bunch of funny business else on here that definitely was not the shortest path, but like it's still extended in the graph? What would happen is, yeah, technically, because this is managed by this while loop, we're going to run through the entire graph, no matter what. But what I am going to pretend and hope that is probably in your brain is like, that seems silly. Shouldn't I just stop as soon as I know I found the shortest path to the thing I'm looking for? Do I really need to get into whatever funny business might be on the graph? And the answer is correct. In fact, what's happening right now is as we're running this algorithm, every time something officially gets to this level and gets pulled from perimeter, whatever its current dis2 is guaranteed to be the shortest possible dis2. So if I eventually encounter my target as I am looping, then I know by the time I get there, I've found the shortest path, and I can break, return, get out of that, so I don't have to do any more unnecessary exploring. Because if you just let this run, remember BFS, it just runs over the whole graph. So this will just actually run, and what it's technically going to do is find the shortest path from every node to source. So you just kind of let it go until you hit the one you're looking for, and then bail if you want to be a little bit more efficient. Did that answer some of your question too? Okay. Yeah, question.
Is there a reason why that distance 2 is stored as a double?
Not particularly. It could be an int in this case, because we're just counting up by 1. I don't know. It's to give you some more flexibility, but it doesn't matter. Okay, great, fine, animations. So the edge2 map stores what we call back pointers. That's probably the part that's so confusing, is you have to kind of recreate the path after you've filled up the map. So really what this code is doing is filling up the edge2 map, and that's your real like important information, and then later you can reverse engineer the path by pulling what you need out of that map. And since obviously we're going to use a hash map, we get constant time lookup, super convenient. Great. Yes, fine. Okay. I think actually this slide says pretty much everything that I was just talking about. So technically what happens, like I said, is it's going to run through the whole map. This pieces of information, these back pointers and these distances, we might refer to this as the shortest path tree. We're just going to use that term. I'm sorry, it's going to come up more times too. And so it's totally up to you if you want to bail early from your algorithm, or if you want to run so that you have the shortest distance from every node to a given source. You can read all this. Okay. So we've talked about connectivity, just can I get in some way between two vertices. Now we've talked about what's the optimal way to get between two vertices on an unweighted graph. What could possibly be next? Welcome to the weighted shortest path algorithm. This is the one that I said is probably the most popular, and this is what we call Dijkstra's algorithm. Dijkstra was a person, and he won the Turing Award, which is like the Nobel Prize, but for computer science, for his algorithm in 1972. But he did a lot of really crazy and important stuff. So shout out to Dijkstra, who actually, only passed pretty recently. What Dijkstra did is he looked at the BFS code and he said, I wonder if we can again add just a few structures and a few intelligent choices and adapt BFS to now give us an answer for the shortest path that will evaluate the weights on a given edge to make intelligent decisions. So here is the basic idea behind Dijkstra's. The idea is very similar to what we just did, where we have a source vertex. We got to pick one place to start from. And then we are going to set the distance from the starting vertex to 0. And then initially, we're going to set the distance to all the other vertices to be infinity. That sort of means like they're so far away, I don't possibly know where they are. And then at each step from each vertex, I am going to look at all of my outgoing edges, and I'm going to ask which one has the lightest weight. What is the shortest way to get to any other unvisited vertex? And I'm going to pick that road. And then I'm going to repeat. When I get to my next closest neighbor, I'm going to look at all of the outgoing edges, and I'm going to say, what's the next closest to me? And I'm going to pick that weight. So we're just going to continually move from closest neighbor to closest neighbor, updating the distances as we possibly examine them until we finally land on the target vertex we're looking for, and then we can bail out. Or we can let it just progress and we can have the shortest path tree if we want. Let's walk through it. So, very similar to BFS, we have a set of things that are, quote, known or processed. We also have the maps from edge 2 and dist 2. We have to do that initialize where everything's set to infinity. You may have to do this in code or you may not, but it's essentially like making that map with all of the vertices in it. Then, this should look really similar to the BFS code. While there are unknown vertices, i.e. while perimeter is not empty, grab the closest unknown vertex, add it to known, then look at all of that vertice's neighbors, get the distances that are currently associated with those neighbors, and compare. Are they currently stored under a larger distance? If so, then update their known distance by my dist2 plus the weight of the edge that connects us. It's a very high level. We're going to get detailed into it. So what's happening here is if I'm starting at A, I look ahead and I see there's two choices to travel to, B and C. And so I'm going to initially set B's dist2 to be 2 and C's dist2 to be 3 because that's the weight it's going to take me to travel there. I will then travel to 2 because it's the shortest one, and then I'll look at B's neighbors and I'll see it's D, and I'll set D's distance to be 2 plus 5, so on and so forth. And I'm always going to make the choice of which node to move to based on who has the smallest distance stored in the dist2 map. What's nice about this is as soon as a vertex is marked known, that means that is its shortest path, locked in. But we might see a vertex more than once because remember, we're standing on one node looking out at my neighbors. So if that vertex has multiple neighbors, I might initially see it as one distance, not choose it because it's not the immediate neighbor, and then eventually work my way around the map somewhere and see a new closer distance to it. It depends on the edge weights. So I know that once I've finally actually navigated to be on that vertex, I've explored all of the possibilities and picked the shortest distance, which is why I can bail in the middle of this algorithm and still be guaranteed that I have the shortest distance. As long as a vertex is not known, as long as it's still like on the other side of my neighbors while I'm looking out, there is a chance that I might find a shorter distance at some point. And so that technically is called relaxing, just to give you some more terminology. Okay, let's talk about runtime. So we know we're going to get some O of V plus E runtime because it's starting with BFS, right? So if that is our foundational runtime, where you know it's at least graph linear. But if we look at the fact that we're using hash sets, we're not really adding anything by adding to the hash set or pulling things out. That's really convenient. Looping and considering all of the vertices from a given vertex, we're going to consider that a worst case scenario of E runtime. And that's like if I ended on some vertex and every single edge happens to come from that vertex off, then this for loop might run in V time, but that's where we get that worst case O of E runtime. But if you look here, technically, everything that I've just discussed does not change the complexity class of this runtime, but there's two lines here that I kind of intentionally left vague. While there's unknown vertices, and let U be the closest unknown vertex. So there's clearly some amount of logic that's happening to pick who is my next closest unknown vertex. And that is going to add some complexity to us. But since we're picking like the smallest in a set, it's almost like we're doing some amount of like sorting. It's like if only we had this like hierarchical structure that would let something say like percolate up to the top. That's the minimum thing I'm looking for. Wouldn't that be convenient? We're going to use a heap minimum priority queue to store each of the unvisited vertices, and it will maintain at its overall root the one with the smallest priority or the smallest distance. So every time we get in the loop, we just remove min off of a min heap. Can anyone remember the runtime for remove min from a priority queue based using a heap underline? Yeah? O of 1. Ooh, so to get min is O of 1, but then we might have to fix it. So you're absolutely right. Log n, absolutely. So, and if you're starting to pick up anytime we have to do sorting, chances are logarithmic's going to run into our runtime. So, yes, we are going to use a heap min priority queue. This pseudocode that's on the page right now, the reason it's not fully code and more pseudocode is because this is P4. I for real, tried to do this line by line. You can copy and paste this into your program and line by line change it so that it will perform Dijkstra's. Also, I didn't really talk about it, but you notice how each of your assignments actually has used the previous assignment inside of it? It's because past Casey thought it would be so cute if all of your assignments built on one another. But guess what? If you had bugs way back in P1, it would make P4 a disaster, so we don't do that anymore. But now I can tell you technically everything you've been building up until this date has been allowing you to be able to run Dijkstra's. We just give you our binaries for them, so none of your bugs screw you for P4 anymore. There's method to the madness, maybe, sometimes. Okay. Okay, so there we go. Here is our final runtime, and those logarithmic runtimes in there, they come from us maintaining a min heap with all of the unvisited vertices in it, removing min, and then doing that percolation back up to fix the min heap. And that logarithmic runtime is going to do that decision factor for where do we go next? What's the next closest unvisited vertex? And that's how we know we're getting to the shortest distance for any given vertex. Because the min heap is just sorting them for us. You're going to practice this algorithm in section, I promise. P4 doesn't even technically come out until next week. It's going to be okay. Any questions so far? Sure.
In the final runtime, there's a E times log. Where is that inside the code?
So that is technically happening down here. And that is because if you vaguely remember when I was talking about the heaps, I was like, there's this other method called update priority that you might have to implement. This is why you have to implement update priority, because as we're navigating through the graph in Dijkstra's, we're going to initially put everything into the heap with the distances that we know them of. But if, as we're progressing, we find a shorter path to that vertex before we're ready to visit it, we need to go into the heap and update that distance. And then it's kind of weird because we're going to jump into the middle of the heap and we're going to change a node. But then we got to let that node kind of work its way to wherever it actually belongs. So I'm going to give you a hint. When you jump into that heap, calling percolations is what kind of helps that thing find its way within the heap. Notice I said percolations. Percolations. Update priority. Multiple percolations. Nobody knows what that means, but maybe when you're really stressed out and you can't figure out how to fix update priority, you'll remember why Casey was being annoying and like cringy in class. Yeah, percolations. So that's where that E log V comes from. Because this for loop runs in E, and then this is a log V within the for loop. Any other questions so far? Let's walk through it mechanically. Okay, so we set the distance of A to 0. Everything else is unknown and infinity. We process A first. We look at all of the outgoing edges from A, and we see that from A, we can get to B, C, and D. We set their dis2 to be the weights of each of those edges, because it's really 0 plus the weight of those edges to get there. And we kind of put A as their possible previous edge 2 pointer. But see how we're still, like they're still not known. We're still looking ahead. But what this means is we now have 3 choices for where to go. B, C, and D. B costs me 2, C costs me 1, D costs me 4. Which one am I going to pick? Which one is going to be at the top of the min heap? Oh, I heard it. C, yes. C, I love it. Yeah, I don't know. Maybe. Yes, we're going to pick C. And now we're going to look at all the outgoing edges from C, and we're going to ask ourselves, where else can we get to? And now we have seen a new vertex, E, and we get the distance of E to be the distance to C, which was 1, plus the weight of that edge, which is 11, so we get 12. Now we have choices. Again, what is the next closest unknown vertex? Our choices are B, D, or E. Where are we going to go? 2, 4, or 12? 2. Yeah, exactly. So we pick 2. And then we look at all of the outgoing edges from B, and we've now discovered a new one, F. And we get that 4 because the distance to B was 2. And then this edge along B to F is 2. So we get 4. So now our choices are 4, 12, or 4. Technically, we could go either of the 4s, but I think I tie break alphabetically. So we go to D. D doesn't have any outgoing edges that like take us to an unknown thing. So now we go to the other 4. But there we go. Now we're at F. F has a new outgoing edge. We finally can have a distance to H. The distance to H is 7, which is the distance to B of 2, and then to F of 4, and then plus that 3, so we get 7. So we're building up the path as we're exploring. Now our choices are between the 12, the infinity, and the 7. Which one are we going to pick? The 7, yeah, there we go. We've got new edges, we do 8. And aha, now we finally found actually a shorter way to get to E by kind of going multiple edges around, and so we end up with this as our final map. So now, if I asked you to give me the shortest path from A to any node, you can do that. So if I asked you for the shortest path from A to E, I would come into my edge 2 map and I would say, okay, E, its previous pointer is G, G's previous pointer is H, H's previous pointer is F, F's previous pointer is B, B's previous pointer is A. And I would recreate that path by working through that map, but it is kind of like reversed in that way. Yeah?
So you mentioned that you can break early when we were just doing like DFT, but you can't really break early doing this, right?
So you can break early in Dijkstra's as soon as you hit the target vertex you're looking for. I just ran it through the whole thing. I didn't even give you a target vertex. But for example, if my target vertex was C or something like that, as soon as I got to C having the Y mark in the known column, then I could have returned or braked or something like that. And like, who cares what the distance is to E or H at that point? Because I just care.
Like, what if you, let's say, like, your first decision is like a weight of 1, and then a weight of 10, but then that one like leads to 1, 1, 1, 1, 1, and then you reach the target, and then that like initial 10 just leads to the target. You would never know that 10 is actually less.
So you will know that it is because this is what's called a greedy algorithm. Let's see, is that the next slide? Yeah. The way that the algorithm is designed is because we're making what's called a greedy decision at every point. We're always going to the next closest. Even in that scenario, we're guaranteed by the time we get to something and mark it as known, that is guaranteed to be the shortest path. Yes. So while it's not known, a shortest path may be found, but once it's marked known, it is guaranteed. We don't care about the order added to the known set. You know, we kind of jumped around a little bit there. That's fine. We need to jump around in order to guarantee that we're always making the best choice possible for our algorithm. And then, of course, this stop early. The reason I am not shutting up about the stop early is because you will be graded on how fast your code runs. And as soon as somebody's like, Casey, my Gradescope test for speed isn't passing, what I'm going to do is I'm going to look in your code and I'm going to see if you stop early. And it's okay if you forget, because 75% of the time, that's the problem. You forgot to stop early. Yeah. Greedy algorithms, yeah. So this is what's called a greedy algorithm. That's how we're guaranteed that by the time we get to something, because at every step of the algorithm, I'm making the best possible instant gratification choice, and those things amortize to be the best one. However, I will finish this on Monday. If I had something like negative edge weights, then I couldn't use a greedy algorithm. Then in that case, there could be a better path out there somewhere, and I couldn't be so instant gratification, Mr. Krabsy. I would have to use something called Bellman-Ford, which we will talk about apparently on Monday. Thank you all so much. I hope you enjoy Dijkstra's because it's going to be a part of your life for many weeks to follow. Yay! Have a great weekend, everyone. See you on Monday.